Actually, TI 4 with stable organ configuration is more stable than TI2 and TI3. So Dr. Ricky Ponting noted this. So while going through the NCERT textbook, he found the exactly reverse of this point. Maybe typographical error in the material. So why TI4? TI has 22 atomic number. So 22 minus 4. 3d2, 4s2. If it loses 4 electrons, it will have 18 electrons, which is stable organ configuration. Thus said, this is more stable. If you have noted this point, make a correction that. Over. Example 17. Just find out mu of spin-only magnetic momentum of divalent ion in aqueous solution of atomic number 25. Atomic number 25 means manganese. Bivalent ion means it should carry 2 plus. So in the plus 2 state, it has 5 unpaired electrons. 5 unpaired electrons. So paramagnetic character, mu is equal to root of n into n plus 2 Bohr magnetons. Here the n value is 5. So root 35. You know, root 36 is 6. Root 35 is around 5.8 or 5.9 like that. So approximately you can do that. Write one more point here. The color exhibited by the ions of the transition metal transition metals depend on the frequency of light which they absorb. Depend on the frequency of light which they absorb. And the frequency of light depends on number one, nature of the ligand. Number 2, size of the metal ion. Number 3, oxidation state of the metal. So actually this we explained already when we considered titanium 3 plus ion with only one unpaired electron. In aqueous medium, in water medium, it is present in the form of TiH2O 6 times 3 plus. Means here the ligands are water molecules. Now Ti3 plus with one unpaired d electron. Initially this unpaired d electron is present in one of the d orbitals. D orbitals initially will have same energy, but 6 water molecules, when they surround the titanium 3 plus ion, this is 3d1. The d orbital split into 2 categories. We already explained this. This is called T2G set. This is called EG set. In EG, how many d orbitals are there? 2 d orbitals, dx square y square and dz square. In T2G, how many d orbitals are there? 3, dxy, dyz, dzx. So it is a lower energy orbital. So the single electron will be present in T2G1. So titanium 3 plus configuration is T2G1 EG0. This is the configuration. Further, normal we say 3D1. But in the presence of 6 water molecules, when the d orbitals split into 2 categories, a higher energy category called EG set, a lower energy category called T2G set. And the single electron definitely occupy the lower energy T2G set, because electrons always want to occupy the lower energy orbitals. Now this will absorb 500 nanometers wavelength of light, or related to 500 nanometers, you can calculate the frequency. So frequency and lambda are related as C is equal to nu lambda. You want to calculate nu, C by lambda. C is velocity of light, 3 into 10 power 10 centimeter per second, by lambda is 500 into 10 power minus 11 centimeters. If you simplify this, you will get frequency. So the nature of light absorbed depends on the frequency of the light that is absorbed depends on the nature of ligand. What is the ligand here? Water. Size of the metal ion and oxidation state of the metal ion. 3 factors determine which wavelength or which frequency will it absorb. When green wavelength is absorbed, this 500 nanometers is related to green color light. So when green wavelength is absorbed in the VIBGR, this green is absorbed. The remaining wavelengths appear in the form of purple color. That's why titanium 3 plus is purple. But I'll give one more beautiful example. So here itself, so here the gap we can use. So Cu SO4 5H2O, copper sulfate pentahydrate. It is called blue vitriol. Blue vitriol. Already regarding this in chemical bond, we have discussed what type of bonds are present in CuSO4 5H2O. That is one type of question. The second type of question asked regarding CuSO4 5H2O. How many water molecules are directly linked to Cu2 plus ion? These are the two questions asked on this. Who will answer? How many water molecules that are directly linked to copper in CuSO4 5H2O? So the answer is 4. Means the copper ion is surrounded by 4 water molecules in the coordination sphere. With copper is having 2 plus. And the sulfate ion joins here with ionic bond. This bond is ionic. Between the square bracket and the sulfate. Between 2 positive, 2 negative. Positive and negative attraction is called electrostatic force. Electrostatic force is called ionic bond or electrovalent bond. Now the last water molecule is linked to the sulfate ion by means of hydrogen bond. So we already discussed this point. But when CuSO4 5H2O is treated with ammonia liquid, it is already blue. We will get a deep blue color. Blue becomes deep blue. So why? Why blue color become deep blue? Because here the weak water ligands are replaced by the moderately strong ammonia ligands. So water molecules are replaced by ammonia ligands. Ammonia is a stronger ligand than water. So that's why the color become deep blue. So it's very, very important. Why CuSO4 blue color copper sulfate become deep blue when ammonia is added? Because a new complex is formed called tetramine copper 2 sulfate. What is the IUPAC name of this? Tetramine. Copper 2 sulfate. So here the important point is why the blue color become deep blue, because the weak water molecules, the weak ligands are replaced by strong ligands. It is a ligand exchange reaction. What it is? Ligand exchange reaction. Here you see some of the colors. Scandium 3 plus is colorless because no unpaired electrons. No unpaired electrons. D electrons. Titanium 4 plus, colorless, same answer. Titanium 3 plus, purple. Vanadium 4 plus, blue. Cr3 plus, Cr3 plus, not violet, dark green. Mn3 plus, violet. Cr2 plus, blue. Mn2 plus, pale pink. Fe3 plus, yellow. Fe2 plus, dull green. Nickel 2 plus, green correct. Blue correct. Colorless correct. So these are the different colors exhibited by the ions of D block in aqueous medium or in the form of salts. Colors are in number 1, the ion in aqueous medium. Number 2, the ion in the form of salts. Only under these conditions they exhibit color. Now, so there is a test, even you study in 8th class, 9th class. Suppose a liquid is given and you are asked to identify that the liquid given is water or not. Sir, I will drink it and say water or not. No. You should not drink because the liquid may be poisonous, may be chemical in nature, may cause burn injuries to your mouth. Anything can happen. So to confirm the given liquid as water, what we do? We take anhydrous cupric sulfate, CuSO4, without water is colorless. It is called anhydrous. Anhydrous means without water. Anhydrous cupric sulfate. Now to this anhydrous cupric sulfate, you added a drop of the given liquid. Drop of the given liquid. If it immediately turns into blue, then the compound formed is CuSO4 5H2. Anhydrous cupric sulfate become hydrated cupric sulfate. What is the color of hydrated cupric sulfate? Blue. Then the given liquid is water. The simple laboratory test to identify whether the given liquid is water or not. Take anhydrous cupric sulfate, which is colorless, add a drop of the given liquid. If it immediately turns into blue color, then the given liquid is definitely water, because the blue color compound formed is copper sulfate pentahydrate. 5 water molecules are there, out of which 4 are directly attached to copper, 1 is attached to sulfate ion by means of intermolecular hydrogen bonds. So this is all about. One more point. Catalytic properties we already discussed. Vanadium pentoxide in contact process, iron in Haber process, hydrogenation of oils, nickel is the catalyst. This one. Fourth one you write. Titanium tetrachloride plus triethyl aluminium. Titanium tetrachloride, TiCl4, and triethyl aluminium. This catalyst is used in the production of polythene. It is called a Ziegler-Natta catalyst. (1963) Nobel Prize in Chemistry for this catalyst. Actually, Ziegler-Natta developed a catalyst, a combination of two compounds. One is titanium tetrachloride, TiCl4. The other is triethyl, C2H5 thrice Al, triethyl aluminium. Actually, this catalyst revolutionized the entire plastic industry. Nowadays, everywhere plastic. The bottle is plastic. Your pen is plastic. The morning toothbrush is plastic. The milk comes from dairy in milk, plastic sachets. So, plastic comb use for your hairdressing. So, everywhere, even the pencil box or pen box you are using is also plastic. There are many plastic chairs here. And this is the fan, the wings of the fan are made of plastic. Your switchboard is plastic. Different plastics. The entire plastic industry, the face of plastic industry is totally changed because of Ziegler-Natta catalyst. So it is so famous. It is used for many polymerization processes of organic molecules to give polymers. So for example, we take ethene, CH2 double bond CH2 plus CH2 double bond CH2 plus if you use titanium tetrachloride plus triethyl aluminium under high temperature, high pressure, this is called addition polymerization. The pi bond will shift like this. This pi bond will shift. This pi bond will shift. So when the pi bond shifts, there is a bond formed between these two units. Because this pi bond is coming in between these two. And this pi bond shifts this like this. That means all the units are joined with each other n times. This is polythene. Polyethylene, called polythene. Polythene is a thermo-elastic plastic. It can be molded, it can be melted. It is not thermosetting plastic like bakelite. Your pressure cooker handle is bakelite handle. Even the pressure cooker is very hot, the handle won't melt, or it won't become soft also. So that is called thermosetting plastics. Plastics are two types: thermosetting plastics, thermoelastic plastics. Polythene is a thermoelastic plastic. Now, MnO2 we already discussed. This one you write. In Wacker's process, palladium chloride is the catalyst. Wacker's process. This is Wacker's process. Actually, we use two catalysts, PdCl2, CuCl2. You will get CH3CHO. You will get aldehyde. It is given in your NCERT textbook. Same name, Wacker's process. In the first year, 11th class, volume 2, organic chemistry, you will find this point in hydrocarbons chapter. And platinum and platinum dioxide, it is called Adams catalyst. It is also used for many purposes. Interstitial compounds. We already mentioned it, they are non-stoichiometric. See the formula of titanium hydride. TiH 1.7. Vanadium hydride 0.56. So these formulae indicate they are not following the normal valency rules. So those compounds which do not obey normal valency rules are called non-stoichiometric. Interstitial compounds, write all the 4 properties, the physical properties of interstitial compounds. High melting points than that of pure metal, very hard, they retain metallic conductivity, they are chemically inert. Properties of interstitial compounds, just mention the 4 points. The high melting point, higher than those of pure metals. They are very hard. They retain metallic conductivity. They are chemically inert. Now in alloy formation, we already discussed about this. Only write German silver, copper 50 to 60%, nickel 10 to 30%, zinc is 20 to 30%, bell metal 80% copper, 20% tin. Gunmetal 80% copper, 10% tin, 2% zinc. You have one alloy called misc metal. 95%? Very good. It is a alloy of lanthanides. That also we'll discuss in lanthanides. Okay. Write the heading potassium dichromate K2Cr2O7. Must. You will get yellow color sodium chromate. Now the sodium chromate is treated with sulfuric acid. It converts into sodium dichromate. This is the second step. From chromite ore, FeCrO2 twice plus Na2CO3 plus O2, sodium chromate, yellow color, plus Fe2O3 plus CO2. Second step is Na2Cr2O7 preparation. In acidic medium, it converts into dichromate. So, chromate to dichromate. CrO4 2 minus 2H plus Cr2O7 2 minus Cr2O7 2 minus plus H2. Most important point is this is chromate. Here I write 2 CrO4 minus. Chromate to dichromate. This is dichromate. Chromate is yellow color. Dichromate is orange color. Due to charge transfer, we already discussed. Due to what? Charge transfer. Now the last step, this sodium dichromate, Na2Cr2O7 is treated with KCl, write 2 KCl, then you will get K2Cr2O7 plus 2 NaCl. Sodium dichromate to potassium dichromate. And here you have to mention this point. Sodium dichromate is more soluble than potassium dichromate. Sodium dichromate is more soluble than potassium dichromate. 3 steps important. You can't escape because these are given in your textbook. We have to follow the textbook. Preparation of dichromate is there. 3 steps. First, chromite ore is fused with sodium carbonate in the presence of oxygen. You will get yellow color sodium chromate. Sodium chromate in acidic medium converts into sodium dichromate. Sodium dichromate is converted into potassium dichromate. 3 steps. Where is this gone?
Left sir, that arrow.
This one?
Left sir, that arrow big arrow. On the left.
The left side of the board, sir. Left side. This arrow, blue arrow. That way.
Oh, this one. Structure of CrO4 minus and Cr2O72 minus, you write. Both structures. But yesterday we have seen one question. What is the hybridization of manganese in MnO4 minus? This point, yesterday we just have seen but not answered. This is permanganate ion. So here manganese is in +7 state. So when manganese is in +7 state, the configuration becomes 3D0 and 4S0. And of course 4P0 also. Now here total number of bonds formed by oxygen atoms are 7 bonds. 2, 2, 2 plus 1. Out of which 3 are pi bonds. So here what happens is, when 4 oxygen bi-negative ions approach, sigma bonds are formed by hybrid orbitals. This is sigma, this is sigma, this is sigma. There are 2 types of hybridization possible. One is sp3, tetrahedral. When this S and 3p hybridize, sp3 will get a tetrahedral structure. The other is 3 d orbitals, 1 s orbital can hybridize. Then the hybridization can become d3s. What is the other possibility? Or sp3. 2 hybridizations are possible, but only one is correct. The correct is D3S, because these are 2 highly energetic. These 3 d orbitals and 1 s orbital, they mix with each other, forming 4 hybrid orbitals. That's why 4 sigma bonds are formed. Sigma bonds are formed by hybrid orbitals only. Pi bonds are formed by pure orbitals. So the remaining 3 pi bonds are formed by pure orbitals of oxygen. So actually this much is not required, just MnO4 minus, the manganese oxidation state is D3S but not sp3. That point only you have to know. Now there is one previous JEE question here. Look at this structure. This is dichromate ion. The bond angle also they have given. And the question is, write the question, the number of equivalent CRO bonds in Cr2O7 2 minus ion is option 1 3, 6, 8, 2. These are the options. So actual option B is correct. The reason is when oxygen is linked with 2 chromium atoms and each chromium atom is linked with one single bonded O minus, 2 double bonded oxygens. This is actual structure with the 2 lone pairs on oxygen. Here oxygen is sp3 hybridized. Because whenever oxygen is having 2 lone pairs, 2 bond pairs, it is sp3 hybridized. Now this negative charge shifts, this pi bond shift. You will get one resonance form. So then this O become minus, this become double bond. In the next step, this minus again come back, this pi bond shifts. So here the negative charge is oscillating on how many oxygens? 3 oxygens here, this side. First this oxygen is carrying minus. In the next step, due to shifting of this bond, so in the next structure, this becomes double bond O. This become O minus. In the next structure, this bond shifts, this bond shifts. Then what will be the structure? This become double bond O. This become single bond O minus. That means the O minus is oscillated among 3 oxygens. They are resonating structures. The resonating bonds are always called equivalent bonds. So here 3 equivalent bonds are there. This side also 3 equivalent bonds are there. So what is the answer now? 6 bonds. So in dichromate structure, how many equivalent CRO bonds are there? 6 are there. Now, write this equation, very important. You may need not by heart the E naught value. Already yesterday we discussed this point. What is the equivalent weight of dichromate ion here? The n factor is 6, m by 6. So dichromate ion in acidic medium accepting 6 electrons Yes, what is your name?
Sowanki.
Spelling?
SOWANKI.
Sowanki. Okay. Somewhat easy to pronounce. Dr. Sawank. Dr. Sawank, in this reaction, electrons are added. The reaction is a reduction reaction. Dichromate is being reduced. The process is called reduction. But in this reduction process, it is accepting 6 electrons. It is acting as an oxidizing agent. So in this process, the +6 state of chromium to +3 state, +6 to +3, oxidation number is decreased. Decrease in oxidation number is called reduction. Or for each chromium to convert its +6 state to +3 state, you have to add 3 electrons. There are 2 chromiums in the Cr2O7 2-. That's why you are adding 6 electrons to convert into 3+. So here N factor is 6. That's why equivalent weight is molecular weight of dichromate by 6. But in this process, since it is accepting electrons, it is a good oxidizing agent. The one which accepts electrons and undergo reduction is called an oxidizing agent. So dichromate is a good oxidizing agent. It oxidizes I- to I2. Suppose if you want to write the entire process, but you don't write actually all these. So already one half reaction is there. Cr2O7 2 minus 14H plus 6 electrons, 2 Cr3 plus 7H2. Now the second one, I minus, gives I2. 2I minus gives I2. To balance, you have to write 2 electrons this side. If you add these 2 half reactions, electrons must be cancelled. That's why I am multiplying this equation with 3, so that the electrons become 6. 6 electrons cancel. So what is the net reaction? Cr2O7 2 minus 14H plus 6I minus gives rise to 2 Cr3 plus 3I2 plus 7H2. That is shortened in the form of this. So dichromate oxidizes I minus to I2. It oxidizes H2S to sulfur. It oxidizes stannous to stannic. It oxidizes ferrous to ferric. Oxidizes NO2 minus nitrite to nitrate. So these are all oxidation reactions of oxidizing properties of potassium dichromate. Potassium dichromate oxidizes I minus to I2. Hydrogen sulfide to sulfur. Stannous to stannic. Ferrous to ferric. What is the last one I added? Nitrite to nitrate. I can add some more. I will add some more here. Primary alcohol to ethyl alcohol We added K2Cr2O7. NCERT book gives Na2Cr2O7. Both are same. H2SO4 gives rise to aldehyde first, followed by carboxylic acid. This is one more extra point. K2Cr2O7 plus H2SO4 plus H2O2. Yes, anyone? We already discussed many times. You will get a blue color chromium peroxide. Blue color chromium peroxide plus K2SO4 plus H2. So hydrogen peroxide plus acidified potassium dichromate. So this orange color dichromate Hope you have tasted the oranges of Meghalaya, Kasi. Kasi oranges. Yes or no? Tasty or sour in taste?
Perfect blend, sir.
Blend of sweet and sour or completely sweet? No, I read about it them. There is an orange festival now going in Assam this week, entire week, where the exhibits of the Mandarin of Kasi and also Sonepur of Assam, the fruits are exhibited there, and the literature says they are very tasty, pulpy, juicy, so on and so forth. They are describing. So I wanted to know the truth from you. If you really tasted Kasi Mandarins rather, pronunciation. So because nowadays so many mandarins are available in our country. Actually, I tasted Californian mandarins. They are very tasty. Because even you need not peel out anything from your mouth, you can swallow them. That much delicate and sweet. But literature describes these Kasi mandarins and the Sonepur mandarins of Assam are equally tasty. So let us see, let us taste and describe. So orange, because when I use the orange color of dichromate. Now Orange Festival is going on this week. That's why I gave that account. So here, this is one more important property of dichromate. I'll give one more very, very important property of potassium dichromate, which is also useful in your qualitative analysis. What is the confirmatory test for chloride ion? Chromyl chloride test. So write that point. Confirmatory test for Cl minus ion in qualitative analysis is chromyl chloride test. Oh, already here they given. This is also given. Knowledge cloud I did not see. Then okay. This one. Just now I discussed this point. Hydrogen peroxide, you will get blue color chromium peroxide. Chromium peroxide is stable only in pyridine. In aqueous solution it decomposes. to Cr3 plus and dioxygen. Actually, this point, which now we highlighted with blue color, is also important. Maybe not at NEET level, but JEE this question. Though I used to discuss this point many times, luckily 1 year this came in the examination. CrO5 and potassium dichromate, sulfuric acid, hydrogen peroxide, all are added, you will get a blue color. The blue color is due to CrO5, chromium peroxide. It has butterfly structure. 4 oxygens have negative -1 oxidation state. This is CrO5 structure. These 4 oxygens will have -1. This oxygen is -2. And chromium will get +6. So when potassium dichromate react with hydrogen peroxide in acidic medium, the blue color chromium peroxide formed will have the same oxidation state as in the reactant potassium dichromate. So here Cr is +6. Here also Cr is +6. There is no change in oxidation number of chromium. But there is change in oxidation number of oxygen. Here all the oxygens are -2. Here 4 oxygens carry -1. So -2 to -1. Increase or decrease? -2 to -1. Increase. Because -2 is a lower number or smaller number than -1. So -2 to -1 it is increase. Increase in oxidation number. That's why here the oxygen is oxidized. When potassium dichromate reacts with, I think for cold, her sleep is gone. You only. She is active now because of the winter. So to keep you active, the season should be very cold. Then obviously she cannot sleep. Because there is no room heaters, etc. So when K2Cr2O7 reacts with hydrogen peroxide in acidic medium, chromium is not oxidized. The oxygen is oxidized. From which state to which state? -2 state to -1 state. Actually, if you keep that CrO5 in the reaction mixer test tube, it again converts into dark green due to the formation of Cr3+. That's why what we do when you carry out this reaction, to keep that blue color intact, we add some ether. Ether is a light liquid, density is less. It is from the upper layer, and the chromium peroxide dissolves in the upper ether layer. Dark red vapors of chromyl chloride. Now, these vapors are passed through NaOH. The solution becomes yellow due to the formation of sodium chromate. This is step 2. This is step 1. What is step 1? The given chloride salt plus potassium dichromate plus sulfuric acid. Immediately from your test tube, which vapors are coming out? Dark red vapors of chromyl chloride. Dark red. CrO2, Cl2. These vapors are passed through NaOH solution. What we do is, actually we keep the two test tubes, one containing NaOH, one containing dark red vapors of chromyl chloride in inclined position. Because one is vapors, the other is liquid. The vapors are coming from this. Because these vapors are heavy, when you keep these two test tubes in incline, this test tube contains NaOH solution. The vapors pass into this. And we close with thumb and shake. The entire solution becomes yellow. The yellow solution, NaOH react with CrO2, Cl2 and form yellow color sodium chromate. This yellow color sodium chromate, in the last step, it is treated with lead acetate. This is acetate ion combining with lead. This is the last step, third step. You will get a bright yellow precipitate of lead chromate. 2CH3COONA. Bright yellow. Precipitate. Arrow downwards. So chromyl chloride test contains three parts. You must read this thoroughly. It is so important. It can come in the dichromate properties, a D block question, or it can be asked as a question from your qualitative analysis. So you have lucky two places, same question. What the test is called? Chromyl chloride test. For identifying which one? For confirming the chloride ion, Cl minus. Suppose I have given a chloride salt to you, like NaCl. You don't know whether it contains Cl minus or not. So to confirm that the given salt is mixed with orange crystals of potassium dichromate, add sulfuric acid and slightly warm heat. Dark red vapors of CrO2, Cl2 are coming out. Then you take another test tube, some NaOH solution, and keep the two test tubes in inclined position. The vapors will pass into NaOH and shake the test tube. The entire NaOH solution becomes yellow color due to the formation of sodium chromate. This is step 2. To this yellow solution, not precipitate, yellow color only, we add a lead acetate solution. Immediately what you will get? A bright yellow precipitate of lead chromate. That confirms Cl minus. Without knowing this point, you should not sit in the NEET examination hall. Third point is also very important. Chromate and dichromate exist in equilibrium at pH is equal to 4. Please write that. Chromate and dichromate exist in equilibrium at pH is equal to 4. Write that equation. 2CrO4 2 minus, here 2 is missed. In the forward direction H plus, reverse direction OH minus. Means chromate and dichromate. CrO4 2 minus. If people can't see, you can write like this. One forward direction H plus, reverse direction OH minus. This reaction occurs at pH is equal to 4. It is in equilibrium. Next we go for, write the heading, potassium permanganate, KMnO4. So potassium permanganate KMnO4. The first step is the word pyrolusite MnO2 is called pyrolusite. Is fused with KOH in the presence of oxygen. Fuse means melted. You will get a dark green color K2MnO4. Plus 2H2. To balance here they wrote 4KOH, 2MnO2. Now it is balanced. Here it is manganese is +4 state. Here it is +6 state. It is called potassium manganate. Now this potassium manganate, after step 1, is treated with the sulfuric acid, acidic medium. It will give to potassium permanganate. It is being oxidized. Plus MnO2 plus H2. Not MnO2, you can write MnSO4 also. Means it is disproportionated. +6 to +7 oxidation, +6 to +2 reduction. Here it is disproportionate. Here they have given ionic equation. +6 here, +6 to +7 and +2, +4. Oh, +6 to +7 oxidation, okay, reduction is. So only 2 steps. Pyrolusite MnO2 fused with KOH in the presence of oxygen. You will get K2MnO4, which is treated with sulfuric acid. You will get potassium permanganate KMnO4, MnSO4 plus H2. This also you write. Industrially, Industrially, potassium permanganate is prepared by electrolysis or electrolytic oxidation. Electrolytic oxidation. So MnO4 2 minus at anode, MnO4 minus plus electron. This is called anodic oxidation. So whenever you want to prepare a large scale, industrial means large scale preparation by this way. Only one point you mentioned. KMnO4 is a good oxidizing agent in acidic, basic or neutral medium. Or neutral medium. Write the heading, important oxidizing properties. Important oxidizing properties of KMnO4. Actually, in acidic medium, MnO4 minus plus H plus gives Mn2 plus H2. Actually, this reaction we have to balance, for which for 4 oxygens we have to write 4 H2 here. Then for 8 hydrogens you have to write 8 H plus. To balance the charges, you have to add 5 electrons here. So left side, 5 electrons you added, 5 negative charges. And MnO4 carries 1 unit of negative. Total 6 negative, 8 positive. Net positive become 2. And this also 2 plus. So this is the basic reaction for oxidizing property of, because it is accepting electrons, Dr. Solanki. Dr. Solanki. Okay, it's easy to remember Solanki. Okay, Solanki. Solanki dynasty is there in history. So, this is the basic reaction. Now I minus is oxidized to I2. I minus to I2. 2I minus 2 electrons. If you want to add these two half reactions, electrons must be cancelled. This must be multiplied with 5. This must be multiplied with 2. So 10 electrons cancel. Then what is the net equation? 2MnO4 minus plus 16H plus 5 into 2, 10I minus gives rise to 2Mn2 plus 5I2 plus 8H2O. That is already given there. But students should not be burdened like that. In a competitive exam, we don't require writing two half reactions, cancelling the electrons, writing the net equation. Even net equation is also not that much required for you, unless otherwise in specific conditions. What you require is, in acidic medium, MnO4 minus permanganate oxidizes I minus to I2. Number 2, ferrous to ferric. This you should know. In acidic medium, I am simplifying this. MnO4 minus oxidizes number 1, I minus to I2. Fe plus 2, ferrous to ferric. Number 3, oxalate to carbon dioxide. But oxalate to carbon dioxide, you should know the entire equation, because you are using in your qualitative analysis, quantitative analysis called volumetric analysis. So that's why I have to write that. What is that? Oxidation of oxalate to carbon dioxide by potassium permanganate in acidic medium. That specially we have to write, because that equation helps you to solve many problems. In this gap, I use this space. So just now we wrote MnO4 minus plus 8H plus 5 electrons gives rise to Mn2 plus 4H2. This we already wrote. Now oxalate is C2O4 2 minus converted into CO2. This also you have to balance. First, to balance oxygen, you have to write 2 CO2. Then only charges you have to balance. 2 negative are there, that's the right side, 2 electrons. So when I add these two, electrons must be cancelled. That's why I am multiplying this with 5, this with 2. So 10 electrons are being cancelled. So the net equation is 2MnO4 minus plus 16H plus 5C2O4 2 minus 2Mn2 plus 10CO2 plus 8H2. And the student should also write this point. 2 moles of permanganate ion are identical equal to 5 moles of oxalate ion, which are identical equal to 10 moles of CO2. If the student remember this line, he can solve many stoichiometric problems. They will ask you how much oxalic acid is oxidized by 1 mole of permanganate in acidic medium. 2 moles are oxidizing 5 moles. 1 mole 2.5 moles. Very simple, no need of writing the equation. Do solve this and that. This line will help you to solve many questions. That's why this equation is having specific importance. That's why I wrote it in a big way. Oh, we already erased that point, no? Again, we go back. Here we are. Here we are. And we are saying that MnO4 minus oxidizes MnO4 minus, in acidic medium oxidizes. This is our center. So I minus 2, I2, ferrous to ferric, oxalate to CO2, S2 minus sulfide ion to free sulfur, sulfite to sulfate, nitrite to nitrate, nitrite to nitrate. You write one more, ferrocyanide, FeCN6, 4 minus, to ferricyanide, 3 minus, ferrocyanide to ferricyanide, these are all oxidizing properties of permanganate in acidic medium. In neutral or basic medium, first one is very, very important. I minus is oxidized to IO3 minus. I minus is oxidized to IO3 minus, iodate ion. Okay, that also will write a chart like this. Only 3 are there. Okay. Only 3 in neutral or basic medium. Permanganate oxidizes I minus ion, iodide ion, to IO3 minus. IO3 minus is called iodate. Dr. Solanki. I minus oxidation number is -1. In IO3 minus, I has +5 state. So -1 to +5 oxidized. And S2O3 2 minus, thiosulfate to sulfate. Thiosulfate to sulfate. Thiosulfate, sulfur is having +2 oxidation state. So +2 to +6. The last one, Mn2 plus, manganese 2 plus ion to manganese dioxide. Be careful, all these are already asked in the examination. All three are very, very important. Write a question here. Why permanganate oxidations are not carried out in HCl medium, in hydrochloric acid medium? So the answer is KMnO4 oxidizes HCl into chlorine. KMnO4 oxidizes HCl into chlorine. Here 2-3 points are important. First point you write, in lanthanides, though +3 state is common, some elements show +2 and +4 oxidation states. Some elements show +2 and +4 oxidation states. For example, promethium, neodymium, terbium and dysprosmium. Which elements? Promethium and configuration. U2 plus is a strong reducing agent as it want to convert into +3 state by losing an electron. Cerium 4 plus, Ce4 plus, strong oxidizing agent, as it takes an electron and convert into Ce plus. Because the common oxidation state is what? +3. So though uranium 2 plus is possible due to F7 configuration, it want to lose an electron and convert into +3 state. Here it is losing electron to get the common state +3 and acting as reducing agent. Here it is gaining an electron to convert its oxidation number from +4 to +3. So Ce4 plus is a very strong oxidizing agent. Europium 2 plus is a good reducing agent. Both of them are acquiring the common oxidation state of +3. This point we already, yesterday we discussed this point. Chemical behavior, earlier members of the series are quite reactive and similar to calcium. But heavier members behave more like aluminum. That point we already discussed. General chemical properties of lanthanides. Only this diagram you also write. Ln represents, Ln is equal to any lanthanoid element. Any lanthanoid element. So here the center, they wrote Ln. Means any lanthanoid element. So these lanthanoid elements with different properties they mentioned. If you add acids, they liberate H2. If you treat with halogen, X2, you will get a lanthanum trihalide, LnX3. With water, they form lanthanum hydroxide and liberate hydrogen. With carbon on heating, you will get a lanthanum carbide. With nitrogen, it is heated, delta. You will get a lanthanum nitride. With the sulfur heated, you will get a lanthanum sulfide. When burnt in oxygen, you will get a lanthanum oxide. Over. Now, second point, an alloy of lanthanoids called mixed metal. Iron 5%, traces of sulfur, carbon, calcium and aluminum. It is used in magnesium based alloy to form bullets. That point is very important. Mixed metal. MISCH. Mixed metal is an alloy. Alloy of lanthanoid metals 95% and 5% iron. 100% is over actually. Traces means small amount. Traces of sulfur, carbon, calcium and aluminum. And it is used for making bullets. This point we just now discussed. Why cerium plus 4 is a good oxidizing agent? Due to high reduction potential. Ce4 plus to Ce3 plus is 1.74 volts. Which is more basic, lutetium hydroxide or cerium hydroxide? The answer is cerium hydroxide. Reason: the earlier members of lanthanoid series resemble calcium, and calcium hydroxide is more basic than aluminum hydroxide. So actinium, thorium, protactinium, uranium, neptunium, plutonium, americium, curium, berkelium, californium, einsteinium, fermium, mendelevium, nobelium, lawrencium. The configurations also we discussed yesterday. So actually actinium, thorium. In thorium also F sublevel not started filling. Protactinium F2 it starts, uranium is F3. Like that it goes on. So though these members resemble that of actinium, they are collectively called as actinoids or actinones. Actinoids or actinones. In these three elements, protactinium, uranium, plutonium, they are used for making nuclear weapons, atom bombs. So whenever you want to make an atom bomb, you should have protactinium or uranium or plutonium. You can't make Even if I give you uranium, you can't make. It requires a lot of technology, and you should have projectiles, the alloys required to keep uranium inside, and also critical mass you should know, you don't know about it. To explode the bomb, atom bomb, the mass initially we take should have a particular value called critical mass. So when all these are not there, you can't make a bomb. Actinide compounds or their ions are colored, most probably due to charge transfer or FF transition. You write the sixth point only. This one. Only one point. Actinide compounds or their ions are colored most probably due to charge transfer or FF transition. First question, we already discussed this question. #21 and 22nd. Why actinide contraction is more than lanthanide contraction? Due to the pore shielding effect of 5f orbital, or the screening effect of 5f orbitals is less than the screening effect of 4f orbitals. Which element show highest oxidation state in actinoids? Neptunium and plutonium. This point we have not yet discussed. So neptunium and plutonium exhibit +7 state. So, additional information. First point we already discussed, charge transfer or electron transfer. Why MnO4 minus purple, CrO42 minus yellow, Cr272 minus orange, that we already discussed. Next one, basic copper acetate is also known as verdigris. This also we discussed. Here some point, Nessler's reagent, I already discussed for confirming ammonium ion. Iodide of Mellon's base also I discussed. Is the entire material coming to your tabs? Yes or no? No, you can download, no? Please do that because some objective questions are there. Whenever you are free, you can work out. If it is allowed. Now after the break we will start this coordination compounds. Our next topic is coordination compounds. Actually, in the coordination compounds, in the D block itself, we have classified the molecular or addition compounds into two types. Please refer your notes. One is double salt, the other is complex salts. So whenever saturated solutions of two different compounds are mixed in 1:1 ratio, you may get two different type of compounds. For example, we take ferrous sulfate, ammonium sulfate, both the saturated solutions in what molar concentration, 1:1 ratio. If you just heat them and cool, on cooling, new crystals are being separated, which we call ferrous ammonium sulfate or Morse salt. Morse salt is a double salt because double salts completely ionize in water. They only exist in solid state or crystalline state. But in aqueous medium, they do not have any existence. Like that, after Morse salt, we discussed alum also, potash alum. For potash alum, what we mix? A saturated solution of potassium sulfate and a saturated solution of aluminum sulfate, boiled and cooled. On cooling, new crystals are being separated. They are called potash alum or common alum. The formula is K2SO4, Al2SO4 thrice, 24H2O. But though it is a new kind of solid that is separated by mixing the two solutions. There the two solutions are added. You got an addition compound. This addition compound can only exist in solid state. But when dissolved, it completely breaks and converts into ions. But in some cases, similarly, we mix two solutions, we get a new compound, but the new compound do not completely ionize. That is called complex compound or coordination compound. For example, in the same notes, same place, you will find another example. A saturated solution of potassium cyanide mixed with a saturated solution of ferrous cyanide, and you boil them and cool, you will get new kind of crystals called K4FeCN6, potassium ferrocyanide. The second example I gave, we take copper sulfate aqueous solution and added liquid ammonia. You got a deep blue color complex. Morning session also we discuss. You got CuNH3 4 times SO4, tetramine copper 2 sulfate. Similarly, silver chloride white precipitate is mixed with ammonia liquid. The precipitate is soluble due to the formation of a new complex, AgNH3 twice Cl. Similarly, I discussed the photographic silver bromide, how it dissolves in sodium thiosulfate or hypo, forming Na3AgS2O3 twice sodium argento thiosulfate. So this entire category, what I am discussing now, those salts which do not completely ionize in water, they partially ionize. For example, if you dissolve K4FeCN6, it won't break into potassium ions, ferrous ions and cyanide ions. It won't give three kind of ions. It give only potassium ions and a new kind of ion called FeCN6 4-. This FeCN6 4- is called ferrocyanide ion. It is called complex ion. And the resulting compound is called complex compound or coordination compound. These coordination compounds play a crucial role in our biological systems, like the vitamin B12, which is methylcobalamin, which manufactures the erythrocytes in the bone marrow. So if you have your RBC, red blood cells are this one less, the hemoglobin levels are less, you get a disease called pernicious anemia. So doctor can easily look at you and tell you are an anemic patient by seeing your eyes, your tongue. They can easily guess or assess you are an anemic patient. Means you are having less RBC. Means your hemoglobin levels are very less. Then you will prescribe some vitamin B12 tablets or injections to fulfill the gap. Because vitamin B12 is a water-soluble vitamin, not like vitamin D, which is water insoluble. So vitamin B12, once upon a time, anemia is very difficult to treat. But nowadays, over-the-counter medicine, you can directly purchase from the medical shop without doctor advice also. If your vitamin B12 levels are low, you can purchase the capsules or tablets and directly take. Even excess of vitamin B12 doesn't harm because it is water soluble, passes through the urine. But vitamin D, higher levels, is dangerous. Low level is danger, higher level also dangerous. All vitamins definitely help the human beings to perform their duties in a proper way. But there is a lot of dispute between the doctors and scientists. Doctors say whatever the substances we eat is sufficient to fulfill our vitamins. Scientists say, especially one scientist called Linus Pauling, who discovered covalent bond. He lived up to 100 years. And he wrote a book on vitamins, Vitamins by Linus Pauling. He's a chemistry Nobel laureate for chemical bond, but for vitamins, he also wrote a book. And according to Pauling, he used to take a lot of vitamin supplements. And his health secret, living such a long time in a healthy way, is because of the excess of vitamins he is taking. But doctors say excess of vitamins cause a disease called avitaminosis, and that is dangerous. We don't know exactly what is true, but there is one American software giant. His name is Brian something. First name is Brian. Now he is around 49 years old. He wants to be like his son. He is 15-year-old. Means he appointed 3-4 nutritionists, 3-4 doctors. He is a multi-billionaire. Lot of money is there. And he is taking the advice from those nutritionists, doctors. When you want to check his body, the MRI of his body should be equal to the MRI of his son. He want to bring back the age, and he want to live forever. That is his experiment, doing on himself, not others. And he is looking young now. If you see the photos, he still looks like young, maybe not 45, or maybe looking like 25 or 35 like that, or 30. But his experiment, whether it become a success or fail, that only time knows. Whether if he lives long with his healthy life, looking like a young man, because he's taking some around 20 types of capsules per day. Some Indian Ayurvedic capsules also is taking, like ashwagandha and all these things. And his sleep is 8 hours sleep, pakka 8 hours. So that sleep also between night 8 p.m. to morning 6 or 5, like that. His sleep is adjusted exactly what the doctors prescribe. In that sleep cycle only he is sleeping. The proteins, vitamins, carbohydrates, fats per day requirement is exactly fulfilling. In addition to, he is taking the vitamin supplements also, with the help of doctors, not himself. We have to see. Recently visited Bombay and gave a big interview to the Times of India. So how he is managing all these things. Lot of money. If Dr. Rudolph is having money, he won't sit here. He will dance, drink, and do a lot of things. So that is the money makes many things, not all the things. Not all the things. So that is the thing. So these play a crucial role. Vitamin B12, which is a cobalt complex, a coordination compound formed by cobalt 3 plus ion. The hemoglobin, which carries your oxygen to different parts of the body, is also an iron 2 plus complex or coordination compound. Even the chlorophyll of green plants we discussed is a magnesium complex. Like that, complexes play a crucial role in our biological systems also. Now these complexes are mainly formed by the D block metal ions because of 3 reasons we already discussed. Due to small size, ionic size, high charge density, and also presence of vacant orbitals. Why the D block metal ions readily form complexes? Because of 3 reasons. What are those? Small ionic size, high charge density, and the presence of vacant orbitals. Not d orbitals, vacant orbitals. It can be d or s or p, whatever it is. Now these coordination compounds are complex compounds. We can also link this point to a question in solutions. Suppose if I ask, which of the following will show maximum elevation of boiling point? Which of the following will show maximum elevation of boiling point or maximum lowering of freezing point, that is depression of freezing point, or maximum osmotic pressure? Suppose if I ask any of the colligative property and give the examples, alternatives, one is Morse salt, the other is potash alum, the other is carnallite, the other is potassium ferrocyanide. Suppose if I give these four options, what is my first option? Morse salt. Second option, potash alum. Second option is potash alum. Third option, carnallite. Fourth option, potassium ferrocyanide. If these four options are given and the question is asked about which will show maximum elevation of boiling point or maximum depression of freezing point or maximum osmotic pressure or maximum lowering of vapor pressure, four colligative properties, which of these alternatives will show maximum? The answer, the one which gives more number of ions, because colligative properties depend on the number of ions. Now the first example, Morse salt, FeSO4 dot NH4 twice SO4 6H2O, give how many ions? FeSO4 give 2 ions, Fe2 plus SO4 2 minus. Next double salt, ammonium sulfate will give 2 ammonium ions, 1 sulfate ion. Total how many ions now? Fe2 plus sulfate, 2 ammonium ions, 1 sulfate, 5 ions will give. Morse salt will give 5 ions. What is the next one? Potash alum. Potassium alum will give how many ions? 2 K plus and 1 sulfate, 3 from potassium sulfate. From aluminum sulfate, 2 plus 3, 2 aluminum ions, 3 sulfate, 5. 5 plus 3, total 8. So potash alum will give 8 ions. What is the next one? Carnallite. KCl, MgCl2, 6H2. KCl will give 2 ions, K plus Cl minus. MgCl2 will give 3 ions, total 5 only. Last one, potassium ferrocyanide. 4 K plus ions, 1 single ion, that is FeCN6 4 minus, total 5. So who is giving maximum number of ions? That will show maximum depression of freezing point. That will show maximum elevation of boiling point. That will show maximum lowering of vapor pressure. That will show maximum osmotic pressure. So here one question is linked to the colligative properties of dilute solutions. So colligative properties are 4 in dilute solutions. What are those? Lowering of vapor pressure, elevation of boiling point, depression of freezing point, osmotic pressure. All these 4 colligative properties are meant for dilute solutions. And these colligative properties depend on the number of ions that substance is furnishing or providing. Okay? Now these coordination compounds, which only partially ionize, look at this. Potassium ferrocyanide, which breaks into potassium ions, ferrocyanide ion. This ferrocyanide ion exists both in solid state and in aqueous solution also. It is in solid state, it is in aqueous solution. So the part that exists both in solid state and in aqueous solution is called complex ion or coordination sphere, which do not further ionize, that won't further break. That is present in both solid state as well as in aqueous solutions. So compounds containing that type of coordination sphere or complex ion are called coordination compounds or complex compounds. Actually, to explain, here already, look at the second point. Coordination entity or coordination sphere or complex ion. Look at this one. COCl3 NH3 thrice. Triamine trichlorido cobalt 3. Okay. Now this complex actually, when you dissolve it in water, it do not ionize. It do not ionize. It is a non-electrolyte because everything is enclosed in square bracket. And something along with the metal, cobalt is the metal here, and some other non-metal species are there. Everything is enclosed in coordination sphere or coordination entity or complex compound, means it won't further break into ions. It exists as a single part. That's why yesterday, Doctor, what is your name?
Tuhima.
Spelling?
Tohima.
T-O-H-I-M-A. Correct? Okay. Dr. Tohima asked this question actually yesterday. She asked the question, because we cover that point also. Here some space is there. She has these alternatives: COCl3 6NH3, first option. COCl3 5NH3 is her second option. COCl3 4NH3, and fourth option COCl3 3NH3. These four options are given. Question is, which will give more number of moles of silver chloride precipitate with excess of AgNO3. AgNO3 aqueous. Actually, when we write this formula like this, without any square bracket, nothing, these are called old formula, Werner formulae. All these are in which mode? Werner formulae. This Werner formulae, we have to convert into modern formulae. Actually, in the Werner formulae, when 3 chlorines are there in all of these, 3 Cl minus are there, cobalt carry +3 oxidation state. So in all these four options, cobalt is in +3 state. In +3 state of cobalt, it always maintains a coordination number of 6. So the first formula, if you convert into modern formula, means cobalt 3 plus must be surrounded by 6 molecules or ions in the square bracket. 6 ammonias are already there. So 6 ammonias surround the cobalt 3 plus ion. This is called coordination sphere. And 3 Cls will be outside. Only outside one will become ionized. So this will break in water into CONH3 6 times. 3 plus 3 Cl minus. With 3 Cl minus, AgNO3 reacts and form 3 moles of AgCl. So first one will give 3 moles of silver chloride precipitate. Similarly, convert the second one into modern formula. Here only 5 NH3s are there. So within the square bracket, CONH3 5 times. Cobalt should maintain coordination number 6. It will request one of the chlorine. My dear chlorine, you stay with me, don't go outside. Stay with me in the square bracket. Don't go outside. Because my coordination number is 6, I have to maintain that in +3 state. So only 2 chlorines will come outside. So it will give only 2 Cl minus ions. Ultimately it will give only 2 moles of AgCl. What about the third one? Now you understand everything. Here only 4 NH3s are there. Cobalt request how many chlorines to remain in the square bracket? 2 chlorines, so that its coordination number becomes 6. Only 1 chlorine will be outside. So in water medium, 1 Cl minus will come. With 1 Cl minus, you will get 1 mole of AgCl. The last one, everything is in the square bracket. 3 ammonias, all 3 chlorines must be enclosed in the bracket, which is called coordination sphere, to maintain the coordination number 6. So it is non-ionizable in water, no ions, with AgNO3, no precipitate. So this is the question. So now you should understand that the coordination compounds contain a central metal ion surrounded by ligands, a central metal ion surrounded by ligands. To balance the charge of the metal ion, some negative ions will be there. So they are called primary valency. So primary valency always satisfy the the oxidation number. Primary valency always satisfy the oxidation number of the metal ion. So based on this, no. You write this one. this representation, central metal atom or ion, ligands. So the ligand's number is 6, that is called coordination number. The entire square bracket is called coordination sphere or coordination entity. Cl3, the counter ions which balance the positive charge of the metal ion. Write the subheading Werner's theory of complexes. Werner's theory of complexes. So the Werner's theory of complexes, first point, the metal atom or ion in a complex. Please write the first point. Werner's theory of complexes. The metal ion or metal atom in a complex exhibits two types of valencies. Two types of valencies, namely, which is non-ionizable. Second point, the primary valencies are always satisfied by the negative ions which corresponds or which satisfy the oxidation number of the metal, ion. And are indicated with dotted lines in the complex. And are indicated with dotted lines in the complex. Next point, the secondary valencies are satisfied by negative ions or neutral molecules or rarely positive ions. Are rarely by positive ions. Full stop. The secondary valencies correspond to the coordination number of the metal ion. The secondary valencies correspond to or satisfy the coordination number of the metal ion and are non-ionizable. I think we already mentioned that. And are non-ionizable and are represented with solid lines in the complex. And are represented with solid lines in the complex. Next point. For any particular metal ion, the coordination number is fixed. For any particular metal ion, the coordination number is fixed. And depending on the coordination number, the complex will get a particular geometry. Depending on the coordination number, the complex will get a particular geometry. Example, in one side you write coordination number, other side you write geometry. Under coordination number you write 2. Under the heading of geometry you write linear. If the coordination number is 2, what is the geometry? Linear. Coordination number 3, trigonal planar. Coordination number 4, tetrahedral or square planar. Tetrahedral or square planar. Coordination number 5, trigonal bipyramidal. Coordination number 6, coordination number 6, octahedral. Next, in some cases, the negative ions satisfy both the primary and secondary valency. In some cases, the negative ions satisfy both the primary and secondary valency. That is, they play a dual role. That is, they play a dual role and are non-ionizable. Next, the number of coordinate covalent bonds that are linked to the central metal ion. The number of coordinate covalent bonds that are linked to the central metal ion or atom is also coordination number. Is also the coordination number. Next point. In the formation of a complex, the negative ions are neutral molecules. In the formation of a complex, the negative ions are neutral molecules which donate electron pairs to the central metal atom or ion. Are known as Lewis bases or ligands. Are known as Lewis bases or ligands, ligands. On the metal ion which accepts the electron pairs is a Lewis acid. And formation of complex is neutralization according to Lewis acid base theory. Neutralization according to Lewis acid base theory. Example, CrNH3 6 times Cl3. In this, chromium shows +3 oxidation state. This is oxidation state, +3. This is primary valence. Because primary valence always corresponds to the oxidation state. These 6 ammonia ligands satisfy the secondary valency. Those which are satisfying the secondary valency is nothing but coordination number. So coordination number is equal to 6. Three Cl minus ions. 3 Cl minus ions satisfy the primary valence. So according to Werner, the metal ion in a complex will have 2 types of valencies. What are those? Primary valency and secondary valency. Primary valency corresponds to the oxidation state and it is always satisfied by negative ions. Secondary valency corresponds to the coordination number. It can be satisfied with either neutral molecules or negative ions or rarely by positive ions. Recent past we discussed about the brown ring complex FeH2O 5 times NOSO4. There in this brown ring complex there is one positive ligand NO plus SO4. Here this is a positive ligand. So ligands can be negative or neutral, rarely positive. But primary valence is always satisfied by negative ions. And the geometry of the complex is not determined by primary valency. The geometry of the complex depends on the coordination number. We have given if the coordination number is 2, the complex is linear. For example, AgNH3 twice Cl Here there are two ligands, coordination number is 2. The silver complex coordination number is 2. Thus it is a linear geometry. What is the shape of AgNH3 twice Cl? It is having a linear geometry. So like this. Now in the coming class we will discuss the classification of ligands. Monodentate, bidentate, tridentate, polydentate, all these we will discuss and continue with coordination compounds.